We'll finish our initial segment on charges and fields with a couple of more example problems. Here's a good one. We have charge Q laying on its side along the x-axis of length A, and we're going to put another charge, a positive charge, little q, a distance r from the end of big Q. So what we want to do is find the electric field that exists in this region out beyond the edge of Q. So let's take this position right here, wherever that is. It's r away from the end of Q. And let's figure out what the electric field is there. So I just put this little band up here, and it's dq or dx. And its distance is x from the origin. That's where it is. X can vary here from 0 to a. And what is the E field along here? So E in the y is 0, hopefully is intuitively obvious right now. And the differential EX, so what's the electric field from this point charge dq at this location? Well, that's pretty simple to set up. It's k q over r squared. So there's k, and then q is dq, and now what's the distance? Well, the distance is a plus this r, but then we have to subtract off this little amount, which is x. So a plus r, but it's not that far away, it's minus x. A plus r minus x is the distance from dq, this particular dq, to the location of the charge. So we square that. Now, q over a, the total amount of charge divided by the total length, is also dq over dx. So we can convert now dq to dx. dq is q over a dx. Hopefully that didn't send you for a loop. This ratio, total charge over total length, is differential charge over differential length. It should be pretty logical, I think. Moving on then, E in the x is, bring out the constants. Now we have dq, which is all this, so there's a q, and there's the a, and 1 over 4 pi epsilon 0 for k, times integral from 0 to a of dx over a plus r minus x squared. All right. What we're going to do is convert this a plus r minus x to this whole thing. Let's just call it u to the minus 2, where u is a plus r minus x, du is minus dx. This is really easy to integrate, which is u to the minus 1 over negative 1, or minus u to the minus 1. And then du is minus dx, so the minus dx brings another minus 1 up there. Those go away. So this cancels, and we know what u is. U to the minus 1 is 1 over this. So q over 4 pi epsilon 0 a, 1 over a plus r minus x from 0 to a. So let's stick a in for x, and a minus a leaves r left. And then putting the 0 in results in a plus r. So this is our result for the electric field at the point anywhere along the x-axis with a positive r. So really it's a function of r at this point. Now let's solve for the force on Q and what that force becomes when the parameter r becomes very large compared to a. So here's the force on Q. It's to the right. Q is a positive charge. And force is equal to E field times Q. We've already worked on the E field though, so we know what that is. We're going to make a little transformation here. This x is a plus r. Okay. So that's where Q is. So r then is x minus a. So the E field is what we had before, but now when we have r, we're replacing it with x minus a. So k, q over a, 1 over x minus a, minus 1 over a plus x minus a. That's that r. And of course, these two things go away. So force, multiply the E field by Q, so here's the constant, times 1 over x minus A minus 1 over x. And there's our force. With respect to x given as shown. And now, when R is much bigger than A, then you probably could guess that as we go a long, long ways away from A, this charge, even though it's laying flat on its side, is going to look more and more like a point charge. I wonder if it would make any difference if this thing was rotated 90 degrees. Well, anyway, F QQ over 4 pi epsilon A 1 over x minus A minus 1 over x. Let's multiply it by 1 over x over 1 over x. Then the top 1 over x, will put an x in the denominator here. So there it is, right here. Takes care of the top fraction. And the bottom fraction, well, if we multiply the stuff inside here in the denominator by 1 over x, it's going to make this 1, and this become a over x, and this becomes 1 as well. So that's 1 over 1 minus a over x minus 1. Well, if you look at, see how this goes, as x goes real big, of course, this x is just inverse. That's an inverse relation with x. When the x gets big here, this comes closer and closer to being 0. So this becomes 1 over 1 minus 1. This approaches 0. In other words, the value gets smaller as x gets bigger, but how exactly that happens may not be real easy to see. So we'll express this as 1 minus a over x to the negative 1 minus 1. And then we're going to apply the binomial expansion to this when x is much greater than a. Now, you don't have to worry about the binomial expansion. I've never seen AP give the requirement of doing something with that, unless they explicitly show you. And I'm not sure that I've seen that either, explicitly shown, like here's the binomial theorem and here's what we want you to do. Well, there's the constant. Well, no, sorry, it's not a constant because we have x. And the first couple terms applied to this, we get 1 plus a over x minus 1. Now, obviously the 1 and the negative 1 go away, so we have a over x. So what this shows is that, to a close approximation, we have our second inverse with x here. So that's QQ over 4 pi epsilon 0 x squared, which is like a point charge, as we would expect. KQ over r squared. KQQ over r squared. For this problem, let's find the electric field at point P as a result of a uniform charge semicircle of charge. Total charge is Q on this thing. So the entire charge on this semicircle is Q. And we want to find the electric field right here at P. Well, here's a dq and a ds. And let's find the contribution from this to our question. And of course, integrate and add up the contribution from all of them. So ds is 80 theta. That's the differential length. A is, of course, is the radius. Linear charge density, as we know, is charge per length. Well, what's the charge? The charge is Q. What's the length? Oh, it's the entire length of the hemisphere, so that's an angle of pi times A. So that's lambda is Q over pi A. And that's dq over 80 theta, because the total charge over the total length is the differential charge over the differential length. Woohoo! So dq, translating dq, since we're not going to be able to integrate with respect to dq, but we will be able to integrate with respect to theta, is q80 theta over pi a. All right, so we've just made the translation. that gives us q over pi d theta, since the a's go away. Now, let's look at the E field produced by this dq at P. We know it's pointing directly away, as shown, and the differential electric field is k q over r squared. Well, q is dq, and the radius is a squared, so that's simple enough. Now, what is a simplification that we can make from symmetry? Well, every dq has a counter dq on the other side, which would make a differential E like this. And of course, the verticals don't cancel there, but the horizontals do. So we have that E and the X is 0. Good, that's taken care of. Now, let's find the differential electric field from this dq in the y direction. We're looking for this part. Well, it's the total amount, k, dq over a squared, times what? Well, it's this component. And it might be easier to look at it from the point of view of, if theta was right here, a small angle, so it was pointing like this, the vertical part of that would be the sine of the angle times a. So it's sine of theta. Sine of theta gives us our answer for the differential E and the y. So E and the y then is k twice integrating from 0 to 2 pi. Okay, that's a certain quantity. We'll double that. 0 to pi, I'm sorry, did I say 2 pi? Well, pi over 2. Sine of theta over a squared dq. So there it is. And the only thing we're going to do now is recognize that dq is q over pi d theta, so we'll stick that in for dq, and we'll be done with the problem. So, EY is 1 over 4 pi epsilon 0 times all the rest that we just got, replacing dq with q over pi d theta. Now let's bring the constants out to the front. There they are. And integral from 0 to pi over 2 of sine of theta d theta, which is negative cosine, from 0 to pi over 2 gives us 0 plus q over 2 pi squared epsilon 0 a squared. So that is our answer. And if we want to replace our 1 over 4 pi epsilon 0 with k, in this particular case, since we have epsilon 0 and 2 pi squared, just saying k makes it look a little simpler. I don't really recommend doing that other than for convenience sake. K broken out into its fundamental parts here is actually more useful. Epsilon 0, for instance, has particular physical meaning for electric field considerations. But there's our examples, and now we'll move on into a very important and wonderfully simplifying tool that we'll have from Frederick Gauss.